Okay, for the first example we're going to look at the hydrohalogenation, where we take an alkene and we're reacting that with something like HBr. Now, it's important to remember as we go along through this that in the first step of most of the reactions we're going to talk about are alkenes either acting as a base or a nucleophile. And we can kind of use the terms interchangeably. Technically it's a base, but it's still acting towards the more cationic or the more electrophilic of the two elements we see on the other side of it. So to begin with, if we've never seen a reaction like this before, well, we have those loosely held pi electrons, so likely electron donor, true of any pi bond we're going to deal with later, with some other caveats with different functional groups. And then we're looking at this reagent, which we know is a strong acid. So we already know the bromine has the lone pairs. We also know that this is heavily polarized like that. So that means we also know that we have partial charges, a cationic on the hydrogen and anionic on the bromine. If this were in water, that bond doesn't even exist. It's already dissociated, but for the moment we're not dealing with that. So we're going to see basically the pi bond acting as a base in this case, going after the more cationic of the two atoms in the molecule adjacent. That's going to cause this bond to break. It's going to break towards the more electronegative atom, so same direction as the dipole moment that I've drawn here. And that's going to give us a question. And that question is, where did it end up? Now, we have two possibilities. Possibility number one is this, that I ended up with the hydrogen, which I'm going to circle just so we're clear. There were already two there, so we just want to make sure we know which one we're talking about. And if that happened, then the other carbon from my original alkene is the one that ends up with a deficiency of electrons. So it had some that it was sharing as part of the pi bond, it now no longer does, so it ends up cationic. That's possibility one. Possibility two is this, that it could have gone on the inner one, to the inner carbon, and given me a cation on the outer one. So this is the question of regiochemistry. We're going to have this question very often. Regiochemically, where does each element end up? In this case, and in many cases, we're going to be able to look at that just based on the cation. Here, and the reason we chose this loaded dice example of a tertiary versus a primary atom, is it makes it really clear here which one of these is a reasonable cation and which one is not. Tertiary cations are extraordinarily stable because of hyperconjugation. Primary cations have a minimal amount of hyperconjugation and therefore typically very unstable. So in this case, this is going to be a yes, no type question. There is going to be very, very little, if any, of product that derives from a cation like the one on the right. Second step, well, now I still have the floating leftover bromine atom as an ion, so it is now fully anionic, and this is now a formal cation. So this is essentially an SN1-like reaction. So easy, does not take a great nucleophile to do it, although the bromine is a very good nucleophile. We don't really need that in this case. Now, we're left with a bromine on the internal carbon and our new hydrogen on the external one. Now, that answers the regiochemistry question, which is basically controlled by the mechanism. Where is the more cationic site? That is going to be least likely to end up with the cationic or partially positively charged element of my two possibilities here. The other is a stereochemistry question. You're going to need to ask that for every example. Do I have control of regiochemistry? And do I have control of stereochemistry? That goes throughout this entire chapter. Regiochemical control? Yes. We do have control of regiochemistry because of cation stability. One is a stable cation, the other one is not. Do we have stereo control? Do we have relative control of stereochemistry? And the answer is no, we don't. Now, we couldn't see that clearly from this example because here, even if I did have that control, I wouldn't be able to see it because of free rotation around this bond, the center one. So, but I'm approaching a cation, which is by definition planar. I have no definition between the top and the bottom. I'm going to get equal amounts of approach on either by the bromide ion. So if I wanted to look at an example where I could see it, I would take a cyclic case and I'll take one with two methyl groups so that I can see where the hydrogen ends up. And what I'm going to end up with when I'm done is this. I'm going to end up with a case where the bromine and one of the methyl groups are in the same direction. And I'm also going to end up with the case of leaving the bromine in the same direction. I'm going to end up with a case where the methyl group and the hydrogen switch places. And each of these will have enantiomers to go with them. So these are the diastereomers, and each of these will be a pair of enantiomers. I have zero control here. So this is the proof that I have no stereo control because I have no possible rotation between the two former alkene carbons. There is no control at all. I get a complete mass mixture of diastereomers, approximately 1-to-1. So absolutely no control, no selectivity whatsoever here. So regio control, yes, because of cation stability. Stereo control, no, because of a formal cation in a stepwise addition.